Hello, today we will have the fifth video. Last time we have range of a linear map, or also known as the image, and then the null space or the kernel of a linear map. Today we will go to the fundamental theorem of linear maps. So this is like important result. So we will prove this. And the next agenda will be matrices. So we will start with recalling we will just recall the operations on matrices such as addition and multiplication of matrices. Okay, theorem. The name is fundamental. Theorem of linear maps. So the theorem is as follows. Suppose we have V is finite dimensional, and our T is an element of the linear map from V to W, set of linear map. The range of T is finite dimensional, and in fact, the dimension of the vector space is equal to the dimension of the null space or the kernel plus the dimension of the range of our linear map T. Proof. Let U1 to UM be a basis for of nullity. Of course, this means that the dimension of T of the null space is equal to M, being the number of elements in the basis. So because this is linear independent, and so here null T is a subspace of what? Of V, and U1 to UM, linear independent, then we can extend your U1 to UM, V1 to VM to N to become basis for our entire vector space V. So this means that the dimension of our V is equal to M plus N. So how do we complete the proof? So we just need to show that the dimension that we want to show now, that the dimension of our range T is just what? N. Okay? So how do we show that? So we want to show this, and then how do we show this? So we have to show that TV1 and then TVN is a basis for our range T. This is what we want to show. Okay. So let V be an element of the vector space V. And then we can write V as linear combination of bases, okay, of U1 plus U2, AU2, then AM, UM plus B1, V1 plus BM, VM. Now, this part here is just linear combination of the elements of the null space. Okay? And then this one is an element of the extension. So what we know is that if it is in the null space, this is just 0. Of course, we have to remark the A's and B's are element of F. So we get T of V. This part here is 0, as I remark, this one. So this is just T of what? Of this part here. T of B1, V1, and then BM, VM. So applying the property of linear map, so we get B1 and then V1 here plus BM, T of BM. Now, this one, this means that the TV1 up to TVM spans range T, and in particular, that is range T is finite dimensional. So we need to show, now we need to show that D1 up to TVM basis for range T. Diba, boy? So because basis, we just have to show its spans range T, which is already shown. And then the next one is we need to show that TV1 up to TVM is linearly independent. Now, suppose that C1, T1 plus Cn, Tn be equal to 0. Then your what? Your T of C1 V1 plus Cn Vn is equal to 0. Hence, your C1 V1 plus Cn Vn is equal, is what? Is in the null space of our linear map. All right? Since this is in the null space, we can say that C1 V1 plus Cn Vn is equal to D1 V1 plus DM VM. Because U1 to UM is a basis for our null T. Of course, these are in F. Okay. Now, what can we say about V1? Recall that V1, Vn, U1, this is U. Right, let me write it again. This is U, this is U, U1 up to UM is literally independent as we have stated earlier. Thus, thus your uh your C's and D's are all zero. That means T1 V1 T of V1 and then T of Vn is what is linearly independent and hence a basis of our range T as needed. So end of proof. So we have dim of V is just dimension of the null space plus the dimension of the range T. So this is just a recall of what we have written earlier because we have not a big board and we can show everything. Now we get some mini theorems here, and these are very easy result. So theorem or proposition, and then if the dimension of V, is, let me write, T be a linear map from V be an element of the linear map from V to W, and then dimension of our V is greater than the dimension of W, then no linear map from V to W is injective. Why? Because this is a bigger space. Our proof runs this way. The dimension of the null T is just the dimension of V minus the dimension of range T. So this is greater than or equal to the dimension of V minus the dimension of W, because the dimension of W is a bigger space. And then this means this is greater than 0. Okay. That means the null of our T is not trivial, hence not no injective map. That means we have the theorem that if the null space is non-trivial, then it's not injective. Since the dimension of nullity is greater than 0, it's not Let me check. Let us recall the dimension of what? Of the nulls of the vector and at the same time we have also a if our dimension this is a continuation if the dimension of V is strictly less than the dimension of W, then no linear map from V to W is surjective. So the proof is apply the fundamental theorem on linear map. That is the dimension of the range is greater than the dimension of W. This is strictly greater than, so so that's it for our linear maps. As easy example of that, recall that if you have a system of linear equations, we have, for example, a homogeneous system. So, of course, example is we get k from 1 to n of a1 and then k and then x sub k equal to 0. Then we get another k from 1 to n and then m k x k equal to 0. So we can think of this as system of homogeneous equations. These are linear equations. Obviously, the solution is the obvious solution is x1 up to x k equal to 0. The question is, are there other solutions? So the answer is using linear maps. So we get to define t from fn to fm, and then t is defined as follows: x1 to xn. This is defined as the first component is just the first linear map, the first equation. And then the last component is mk x k. And then the equation t of x1 to x n equal to 0 is the same as this system of linear equation above. So what is the condition to show what is the condition that ensures T is not injective? So the following is our result. This is a familiar theorem from before if you have taken a course in basic linear matrices and operation. Homogeneous system of linear equations with more variables than equations has non-zero solutions. Okay. So that is, if you get a matrix, you cannot reduce the number of if you have more equations than matrix, then you get other solutions aside from the trivial ones. So a short proof is just application of the linear map from Fn to double Fm. And then we have n variables. And then because n is greater than m, we have proof outline n is greater than m. N is the number of equations. N is the number of variables. Number of variables. In this case, it's x1 to xn, and then here m is number of equations. So in this case, dimension of our the dimension of our null space is greater than 0. Thus, we have non-injectivity. And lastly, if you have let me write it in like a1 uh 1x1 plus a1 nxn, and then am1x1 plus amnxn equal to let's say b1 and then bm. So we have an inhomogeneous system with more than more equations. So here, if m is greater than n, then more equations than variables, then what? Has no solution for some choice of constant terms. Recall this one from your matrix course. So there's for some choice of constant terms, we will get like 1 is equal to 4. So that's a contradiction. So there's no solutions. Something like that. Now we go to matrices. So what's a matrix? This is the same chapter. And then the section is titled matrices. So what's a matrix? Define. I will not define, I will just set A. This is our matrix. This is A11, and then A1N, and then AM1, and then AMN. There's a comma here. And then this is a rectangular array. So the array has M by N array, M number of rows, and N columns. And then the AJK here is the entry in J row and K column of our matrix A. For example, we have our matrix ilang rows to? 2, and then number of columns is 4. So 8, 4, 5, 3i, and then 1, 9, 0, 7. So this is complex number. So your A 2, 3. So A 2 row and 3 is equal to 7. So 2 row 2 column 3 is 7. Okay. So how do we define a matrix of a linear map? So suppose that T is a linear map from the vector space B to W, and then V1 to Vn, bases of V, and then W1 to Wm, bases of W. The matrix of our T with respect to these bases is the M by N matrix. MP, whose entries A, J, K are defined by the following. T of VK is equal to A1K W1 plus AMKWM. And then if the bases are not clear, we write M and then P here, and then the first basis V1 to Vn. The second basis, the basis of vector space W, we write also. So that's the notation. So the matrix of the linear map depends on the choice of basis for V and W. All right. So this is how we write this. So the matrix of the linear map T, it's just you write W1 up to Wm, and then V1, and then Vk here, and then Vn, and then this is A1K, and then we end with AMK. So this is the, recall the TVK. We just write this as A1K W1 plus AMK WM. So here goes here, here goes here, and everything, it goes in between. And then this, let me change color. This W1 are these ones and these ones, and then the VKs are above. Okay. So we have what we call the standard basis. If not mentioned, we will use the standard basis of Fm. So what's the standard basis? So this is just 1 and then 0 all else, and then 0, 1, 0 all else, and then 0, 0, 1, and then 0 all else. We call this definition of standard basis. Now let us consider an example of a linear map. So suppose that this is an example. Suppose that we get a linear map from F2 to F3. And then this is defined as follows. So this is x plus 3y, and then 2x plus 5y, and then 7x plus 9y. Find the matrix with respect to standard basis of Fn, or F2 and F3. So now, how do we do that? The solution T of 1, 0 is equal to apply here. So the first component is 1, the second component is 2, and the third component is 0. And then T of 0, 1 is just 3, and then 5, and then 9. So the matrix M of MT, we just write this is our base 1, and then this is our base 2, then W1, W2, and W3. So with respect to the first, the bases, W1, so we get 1, 1, 2, 0. So okay, this is not 0. This is 7. This is 7. The 7 here. So for the first, we have this 1, 2, 7, and then 3, 5, 9. That is T of V1 is equal to 1 times 1, 0, 0 plus 2 times 0, 1, 0 plus 7 times 0, 0, 1. And T of V1 here is, what's V1? 1, 0. And then V2 is 0, 1 basis of F2. And then the other one is 3, same, plus 5 plus 9. And then we write it this way. This way. All right. That's an example of our matrix of a linear map. Now we will go to the familiar notion of recall. I will not be defining them. So addition of matrices. And then suppose we have a matrix A, matrix with Aij, and matrix with Bij. So the matrix addition is Ij plus Bij. So we just add component twice. And then if lambda is some scalar, and then we also recall the matrix of linear map. I will not be proving this. S and T be two linear maps. Your linear map, your matrix S plus T is equal to the matrix of S plus the matrix of T. Also, recall the scalar multiplication. Suppose for all lambda in F, your lambda times matrix Aij is equal to lambda Aij. You just multiply component by component with all the components with lambda, and the associated result is the following: lambda in F and then T in a linear map from V to W, the matrix of lambda T is equal to lambda times the matrix of T. All right. Now, this is like not really the notation for many courses. So in our reference, we have FMN. This is the set of M by N matrices over our field F. But sometimes this is denoted as M by N over F. Other notation. And then the theorem, the dimension of FMN is equal to Mn, M times N. So yeah, that's it. So the outline of the proof is the following. So this one, and then 0, 1 in 1 and 3, 0 all else is an element verify that this spans DMN or FMN. Of course, we already know matrix multiplication. And if we have A, C, I, J, J, K, so here we have A, B, M by N, matrix, C, B, and N by P matrix. Note that N here, this, the here and here should be the same. Then the matrix A, C, J, K. This is just the sum of A, J, R, and C, R, K, R from 1 to N. So this is like complicated to write, but this is easy to recall by doing example here. So example, we have 1, 2, 3, 4, 5, 6, and then we get 6, 6, 5, 4, 3, 2, 1, 0, negative 1. So the first entry is this multiplied with this. Now, it's just multiplying this one with this and this. So the first entry here is 1 times 6 plus 2 times 2, which is 10. So dito ay 10. Second entry here is this times this. So 1 times 5 plus 2 times 1. So this is 7. So 10, 7, and then 4, and then 1, and then you write the rest. Okay? So of course, associated with the parallel result above, if we have a linear map from B to W, and S be a linear map from W to okay, let's change letters. This is U to V and V to W. From U to V and then from V to W. Then your matrix of S times T is equal to the multiplication of matrix of S times the matrix of the linear map T. I will leave the proof as exercise. Now we have some special notation. So for example, we have your A here is 845 and then 197. We write A2 dot. It's just this is row 2 of A, and then A dot 2 is column 2 of our matrix A. In this case, A2 dot is just 197, and A dot, and then 2 is equal to 4, 9. So just this is A J dot is the jth row of A, and then A dot K is the kth column of our matrix A. Okay. So the other results are left as reading assignment. So linear combination of columns. So A is M by N matrix, and C be N by 1 matrix. AC is linear combination of columns of A with scalars that multiply the column vector from our C. So okay. I think I will leave it here for matrix with linear maps. Next time we will go to the results are easy to follow, and then it's left for reading assignment. So next meeting we will consider isomorphism of vector spaces. And then after isomorphism of vector spaces, we go to some details on matrices on invertible maps, and then the invariant dimension property, And then linear map thought of as matrix multiplication and some more theorem, but this is the main topic for the next meeting. So I think I'll end this recording at this part here.